This is a recording for math analysis, and it's for section 4-2 degrees and radians. I have to apologize because in all of this unique situation that we have, I do not have all of my files at home, and that's where I'm recording this from. So I'm actually starting a new file. I do have the beginning of this lesson on my Yola site, and but I'm just going to kind of restart this one. And I also have to say that I did not allow enough time in my plan probably for this lesson. So I also am just going to forge ahead and not make any changes, and we'll just kind of down the road change things if we need to. So just a reminder, by now, hopefully you know some of my expectations, and for each section, I will be expecting you to take notes still, and for each section, I'll essentially want the heading and the essential questions. So can you convert degree measures of angles to radians and vice versa, and use angle measures to solve real world problems. And then handwritten work for examples, as we usually do. And so that's going to be my expectation. If you want to write the essential or your level of understanding, that would be awesome, but it is not necessarily something that I will be holding you accountable for. Also, when I write in yellow like that, I usually am going to be erasing that as we go. So this first part of the lesson, I'll go through a little bit more quickly, just because I do feel like I have done that already. So just a reminder, if you were in class, that we said an angle is defined as two non-collinear rays, and with a common endpoint. The common endpoint is the vertex, and that angle has an initial side and a terminal side. And when it's in, and so this is the picture of that, and hopefully you've drawn that in your notes at some point. This should be in your notes. And then an angle in standard position now is what we're going to also be looking at. And again, this is just kind of recapping some things that we have looked at before. The standard position of an angle means that the initial side, let me write in yellow. As you're writing this picture, if you haven't already, that the initial side is on the positive x-axis. The terminal side can be anywhere. Think of it as like almost a spinner. And if it goes counterclockwise, what like this, that is a positive angle. And so that I will write in here that was this is a positive angle. And in class, I also just drew another picture, and I'll just slide that in right here. That is if we have a standard position angle, and so that positive x-axis and maybe that terminal side is in the same place, but that we go clockwise along there, that is going to be a negative angle, negative angle. And so we also wrote that on I also had that written on my original slides. Feel free to pause things as you go. And so this is just the positive and negative. And you can read through those either on the completed slides PDF or by playing this recording as you go. So we're pretty familiar with the concept of degrees. And so a degree, which has that little notation there as well, is equivalent to 1/360th of a full rotation. And notice it also says counterclockwise about a vertex. And there's a nice little illustrative picture there as well. And then degrees can also be written in several ways. Degree measures, they can be written as decimal degrees or in degrees, minutes, and seconds. And so degrees, minutes, and seconds, often abbreviated DMS. And you can read those notations there as well. And then I am just going to add in what I already had on my notes. 1 degree is equal to 60 minutes. It's kind of like a clock thing. And the marking for a minute is just a little hash mark like that. And 1 minute is equal to 60 seconds, also just like a clock kind of thought. And that it uses a little double hash mark. And then 1 degree would be if 1 degree is 60 minutes, 1 minute is 60 seconds, so 1 degree is also 3,600 seconds. So the 60 times 60 seconds. And so then if we have 32.5 degrees, that's like 32 plus 0.5. And then we can change that into minutes by taking that 0.5 times 60. So it would be 32 degrees and 30 minutes. Just to kind of think about that and using that kind of clock again way of attacking things. So then this one I was also done with, and so I will just write what I have on that other file. 1A, and we're going to change from decimal degrees to degrees, minutes, and seconds. My apologies for my handwriting right now. I'm doing the best I can. So this is 329.125 degrees. So what we're going to do is rewrite it as kind of the 329 plus 0.125. And then we're going to take that 1.125 and we're going to multiply that by 60. And then that'll be 329 degrees plus 7.5 minutes. And then we're going to take that 0.5 again, and so we've got the 329 degrees plus 7 minutes plus 0.5. And since we've already multiplied by 60 one time, to get it to minutes, we'll multiply just that decimal by 60 again to get it into seconds. So that gives us 329 degrees, 7 minutes, and then rounding to the nearest second, but it's whole number here, 30 seconds as we go. Then for number 2, kind of going from degrees, minutes, and seconds into decimal degrees, and I hadn't finished this one several weeks ago when that was 1B, and that's from degrees, minutes, and seconds to decimal degrees. So 35 degrees, 12 minutes, 7 seconds. So we're going to take that 35 plus 12 times and 1 over 60 plus 7 times 1 over 3,600. And when we do that, then we're going to get for that one, let me see, 35 plus, or excuse me, not plus this time. Ooh, sorry. There we go. Let me just get the eraser a minute. And you can just type that all in your calculator in one motion, so to speak, one set of calculations. So 35.202 degrees for that one. And now we're just moving on through the rest of the lesson. Now it talks about radians, and radians are something I would be asking you about your familiarity, but right now we'll just kind of go through that. And so this is radian measure, and in symbols is what I'm going to ask that you write for sure. Just one moment. So I will read it in words. The measure, but symbols is what I'll ask you to write in your notes. The measure theta in radians of a central angle of a circle is equal to the ratio of the length of the intercepted arc S to the radius of the circle. And so theta equals S divided by R, where theta is measured in radians. And sometimes that's abbreviated RAD. And so I will be using that abbreviation as well. Let me RAD. And theta, if that's new to you, that's just a Greek alphabet letter to kind of name that. And just as a little justification or something to notice, so if we have that angle or a circle, and we're kind of thinking about going around that circle. Imagine a minute for the radius to be 1. And so if we go all the way around, that's 2 pi. So circumference equals 2 pi r. If we think of that radius as 1 for a minute, the circumference is equal to 2 pi. So all the way around is 2 pi. And then the theta that we're going to find is going to equal S. And a lot of times I use a cursive S over R as we look at that. And so that is that arc as we go. Theta equals 1 radian when S is equal to R, kind of as we go. Now, the ratio of S over R is unitless, and that is why we prefer radians to degrees in a lot of applications, because then we don't have that unit that we have to kind of think about. This slide is just for you to look at central angles, and so just kind of thinking about, and you don't have to write all this down, and below that dashed line we'll write maybe some things, but 2 pi radians, I'll just try to use my yellow marker. A full revolution, pi is half of that revolution, and you will want to kind of think about that. Pi over 2 is a fourth of a revolution, and pi over 3 is 1/6 actually of that rotation. And so when you think about that, and let me get rid of those a minute, except for this first one. And so remember, this is 360 degrees around a circle, and now it's 2 pi. So that means that 2 pi radians and 360 degrees both correspond to a single revolution. Oops. And so then kind of reducing that, 360 degrees equals 2 pi, so 180 equals pi radians. And then we can get some conversion rules. And I will ask that you write these conversion rules as you go. So to convert from, and I'm going to maybe, let me slide that down a little bit. This I do want you to write something for, and the way I'm going to write it is if we go from degrees to radians, we take the degrees times pi over 180 radians. And a lot of times we leave that pi in there, but we don't write that RAD part. And likewise, if we're going to go from radians to degrees, we take our radians times 180 divided by pi degrees. And so they give you some little things. You can read those if you want. Make sure that you're using the degree symbol if it's in degrees, because we will have an expectation that we have that kind of as intended. So then a lot of times, like I said before, we want to use pi in our answer. And so this 2a problem is 135 degrees, and we want to convert it into radians. So we're going to go from degrees to radians. And then in this case, we'll take 135 times pi over 180. And then we get 135 over 180 pi. Just a little note to self, a lot of times we leave that pi in there, but we also a lot of times take this fractional part and convert that into a reduced fraction. And so I just am really familiar with this. I know 45 will go about into each of those. So, 45 goes into 135 3 times and 180 4 times. And so 3 times pi, 3 over 4 pi, or 3 pi over 4 is how we would write that. And again, now it's in radians, so we don't usually use any label on that. And so again, even if it's negative, so 2b here is negative 30 degrees. And so I'm going to take my negative 30 degrees times pi over 180. And so that's negative 30 over 180 times pi, and that's negative 1/6 pi, and that's negative pi over 6. So pretty straightforward as we do that. If you'd like to try this next one, just pause the recording and then try it, and then we'll move on. So this is 2c, and that is, now we're going from 2 pi over 3, and we're going to from radians, to degrees. And so if you want to pause this and try that one, go ahead and do that. Otherwise, I'll move on. So 2 pi over 3 times, now when we're going from radians to degrees, we multiply by 180 over pi. Notice in this one, those pi's are going to cancel out, and that is often going to be the case, and but not always exclusively. And so 2 times 180 divided by 3 is 120. Now it's in degrees, so make sure you write that little degree symbol as you go. Then we have another one that we're going to start in radians and change it to degrees. So 2d, this is negative 3 pi over 4. And we're going to go again from radians to degrees. And so this time we're going to take that times 180 over pi. And again, our pi's will cancel in this one. And then negative 3 times 180 divided by 4 is negative 135. And again, degrees, so make sure you write your degree symbol there as we go. Then our next topic that we want to talk about is coterminal angles. And so coterminal angles, let me do a little better job on that. Coterminal angles, and they have the same initial side, same terminal side, but different measures. And so what we can kind of think about, and we'll maybe just kind of draw a few little pictures up in the corner here. And so just a reminder, when we've got that standard position angle, we've got the initial side is on the positive x-axis, and the terminal side can be anywhere. And so if I kind of think about, and I'll just draw several little sets of axes here, and I'm going to draw that same initial and terminal side, but a bunch of different angle measures. So I'll just pretend those look about the same as I go. And then I'm going to show by my rotation what kind of angles these are. So this first one, will just be that positive, maybe acute angle it looks like it might be, and less than one rotation. A second angle might have this same initial side and do a complete revolution and then go over to that terminal side. So kind of adding either 360 or 2 pi, depending on whether you're working in radians or degrees. Another way might be to have that negative angle, which is less than one full revolution again. And another possibility would be to do a negative revolution and then to that terminal side. So a negative angle in these last two, and where we've subtracted an extra kind of 360 as we go. And sometimes we call these angles alpha and beta, just to kind of let you know that. And so now we want to write something about coterminal angles. And if alpha, which is again Greek alphabet, is the degree measure of an angle, then all angles measuring alpha plus 360 n degrees, where n is an integer, are coterminal. So alpha is the degree measure of an angle, then alpha plus 360 times n degrees, where n is an integer, are coterminal with A. And that's in degrees. Then in radians, and maybe we should say that. And then in radians, if alpha is the radian measure, then alpha plus 2, and the book authors say 2n pi. I tend to say 2 pi n, where n is an integer, are coterminal with alpha as well. And I just like to maybe write a little extra here. So let me just write my own little wordiness there. And so I'm going to say alpha is the original angle in degrees, and then all coterminal angles are alpha plus 360 n degrees, where n is an integer. N is integer. And then likewise, if we're writing in radians, so alpha is the original angle in radians, and then all coterminal angles are alpha plus, and this is just my way of doing this. I like to go 2 pi n, where n is an integer. And the book authors kind of put that pi second. So either notation is perfectly fine. I'm just going to tell you that that's what I default to as I go. So then in 3A, we're going to identify all the angles that are coterminal with 80 degrees. And we're going to find and draw one positive and one negative angle coterminal with 80 degrees. So I'm going to say that this is 3A. And we're having an 80-degree angle. And first, I'm going to do all coterminal angles. All coterminal angles. All coterminal angles. And so since this is in degrees, all the coterminal angles would be 3 or 80. There we go. 80 plus 360 n degrees. 80 degrees plus 360 n. So that's all of the ones that are coterminal. And then it didn't ask us necessarily to draw the original angle, but I'm going to draw 3 pictures. I'm going to draw the original, a positive coterminal angle, and a negative coterminal angle. So I'll put 3 sets of axes right there. And so my original angle 80 degrees, and as long as you have it in the right quadrant, you don't have to be super careful about how you draw that, and especially at these times. So the angles all have to be coterminal, so I'm just going to draw them in there. And then I'm going to get a positive coterminal angle by putting in my little formula there, 1. So 80 plus 360 times 1 is 440 degrees. Oh, not 444, just 440 degrees. And you can verify that with a calculator. If I make errors, a lot of times I find them, but just know that that does happen for me. And then showing these, I'm sorry I didn't put that little arrow in the first one, but this one I do a whole revolution and then go back to here. And then for the negative one, I'm going to go 80 plus 360 times, and n is an integer, so this time I'm going to put in -1. So in a way, that's like 80 minus 360, and so that's negative 280 degrees. And again, that's a full negative revolution, and oops, not a full negative revolution. So it's a, oh, not sure what I did there. So there we go. It's a negative revolution to right there, negative 280 degrees. Now, in this instance, that 80 was an acute angle, and it was kind of that smallest original angle that we could have. Keep in mind, if instead of 80, we had been given 440, we would maybe have to subtract 360 and then subtract 360 again in order to get a negative value as we go. So now that we did one of those in degrees, which are probably more familiar to us, now we're going to use radians. So this is 3b, the same thing, and our original angle is negative pi over 4. And so first thing I'm going to do is all coterminal. And notice this time it's going to be negative pi over 4 plus 2 pi n. And I'll put a little box around that because that's going to just help me know how to get other angles as we look at this. And again, I'm going to do the 3 little pictures here. And let's see if I can slide that down quite a bit. So now I'm going to do those in a different color. And so the negative pi over 4, initial side is the positive x-axis. It's going to go down like that. I'll put my little arrow there. And so this is our original negative pi over 4. So now I know where the initial and terminal sides are going to be as we look at that. And then to get a positive value, if I can, I'm going to take my negative pi over 4 plus 2 pi times 1. And I am going to practice getting a common denominator because you're going to find that if you get a little bit more comfortable with fractions and getting that common denominator, it'll be a little bit easier for you. So I'm going to multiply this by 4 over 4. So that's going to be my negative pi over 4 plus 8 pi over 4. And that's going to give me 7 pi over 4. So there's one positive coterminal angle. And really then, if I think about getting to 7 pi over 4, I would just go this way, positive, and I'd get that angle measure. Now I need a negative. I already have my original, in this case, is negative pi over 4. And so this time I'm going to subtract 2 pi times 1 in this case. So I'll get negative pi over 4 minus, and again, I'll get that common denominator, 8 pi over 4. And this is negative 9 pi over 4. And I am just gonna kind of tell you how I count this out, and I'll move some of this as we go. I kind of think about this circle concept and kind of that rotation around, and kind of getting to right there. And I can kind of count that by pi over 4s using my axes. So I'm at 0 there, and then I'm at 2 pi over 4, and then I'm at 4 pi over 4, and then I'm at 6 pi over 4, and oh, I'm sorry, my apologies, the wrong way. So I'm at 0, negative 2 pi over 4, negative 4 pi over 4, negative 6 pi over 4, negative 8 pi over 4, and then one more as negative 9 pi over 4. My apologies for going negative there, or positive instead of negative. And so when I draw this one in, because I'm going negative, it'll go all the way around and then to right there. So those are my angles. Also notice if I had wanted to give this, and I'll write in yellow a minute and then erase it. If I had wanted to give this angle as a positive angle, that really the first positive angle would be this one. So this could also have been written as 7 pi over 4 plus 2 pi n. And so notice, notice I had written minus 2 pi times 1. I could have written that as plus 2 pi times negative 1 and gotten the same result there as we go. But just something to keep in mind as we look at a problem like that. Then the next part of this lesson is about arc length. And so let me ask that you write some things about arc length. So I'll circle that arc length. And if theta is the central angle in a circle of radius r, then the length of the intercepted arc s is given by s equals r theta. And I'm maybe just gonna, let me get rid of that a minute. I am gonna recircle that. So if you wrote it down, awesome for you. I'm just looking for my slide a little bit here. Oh, I think I just changed something about how it is written there. That's all right. So my circle might not look like a circle completely at this moment, but let me just move things around a little bit so that I can have a little bit of space on here as we go. And so now I'll go back to some highlighting. So arc length, you're going to write that down. And let me use this so it's a little easier for me to do. If theta is the central angle in a circle and r is the radius with radius r, then the length of the intercepted arc s is given by s equals r theta. And please make sure you write this, that theta is measured in radians. And so now I'm maybe just going to write a few things on here as well by hand. So theta is equal to the central angle in radians and r is the radius. And if you remember from before, and it says this kind of way up here as well, but we've said theta equals s divided by r. And so if you think about solving that for s, you would get r theta equals s. And so just keep in mind that s is equal to the length of the intercepted arc, length of intercepted arc. And so we write it this way: S equals R theta as we go. So now we'll look at kind of some application problems for that. So this is 4A, and it says find the length of the intercepted arc in a circle with a central angle measure of pi over 3 and a radius of 4 inches and round to the nearest tenth. So we know S is equal to R theta, and in this case R is 4 inches. Theta is pi over 3. So S is equal to 4 times pi over 3. And it did ask us to round to the nearest tenth. So that means we can write that S is approximately equal to, and when we use a calculator, 4.2, and we'll label that as inches. So that one's pretty straightforward in terms of that. And just a reminder, theta has to be in radians, and it is there. Now for 4b, it says 4b, find the length of the intercepted arc in a circle with a central angle measure of 125 degrees and a radius that is 7 centimeters. So for this one, our theta is 125 degrees, and our radius is 7 centimeters. And we know that S equals R theta, but our theta has to be in radians. So this one is not. So we have to convert it to radians. And so theta is equal to 125 times pi over 180. And, you know, in this one, I'm not really going to reduce that because I'm just going to use it as a part of a calculation here. So I'm just going to say it's 125 pi over 180. And then I can just substitute that in. R is 7, and theta is 125 pi over 180. And then to get my S value that I want here, let me just slide down a little bit. So S is approximately equal to, and again, rounding to the nearest tenth, 15.3, and in this case, centimeters as we go. So that is finding the arc length. Now, the next little part is about linear and angular speeds. And I know this lesson is getting long, but I am just going to forge ahead on this one. And then I will try to break things down a little bit as time goes on. So the rate at which an object moves along a circular path is called its linear speed. And the rate at which an object rotates about a fixed point is called its angular speed. So linear speed, and I'll change my color here just a moment. So linear speed is measured in units like miles per hour, whereas angular speed is measured in units like revolutions per minute. So just kind of something to be aware of. So linear and angular speed is what we're talking about. And I am going to use some space below here to kind of write what's happening. So it says, suppose an object moves at a constant speed along a circular path of radius r. If s is the arc length traveled by the object during time t, then the object's linear speed, v, is given by v equals s divided by t. If theta is an angle of rotation in radians through which the object moves during time t, then its angular speed, omega, and that's a Greek letter of the alphabet, is given by omega equals theta divided by t. So what I'm going to ask you to write, and I'm going to kind of write it below here a little bit, and that is that the linear speed, which is v, v is equal to s divided by t. But remember, S is r theta, so we can call it r theta over t as well. And linear speed, let me just kind of see if I can slide this down a little bit. And linear speed is the rate of the object moves along a circular path. And it might be given in miles per hour. So that's kind of something that you're familiar with. And then the angular speed, which is this kind of, curly W omega. And let me just move that a little bit out of the way. There we go. Omega is the rate, and omega is equal to theta over t. And so that is the rate an object rotates about a fixed point. Oh, I don't think I spelled about correctly. A fixed point. And it may be given in revolutions per minute or RPMs as we look at that. And so one thing I'm just going to have you notice right now is that angular speed, which is theta divided by t, if we write this version of our linear speed, notice that theta divided by t is there. So an alternate version we could give here, is v equals, and I didn't do, is v equals r times omega. And I'm not going to write that right now, but I just want you to keep that in your mind as we move forward. So then we're going to look at kind of an old-time problem, so to speak. And that is, let me move on here to, this is 5A. And it says a typical vinyl record has a diameter of 30 centimeters. So this is kind of an old-time question, but kind of that retro turntable kind of records has kind of made a little comeback in some venues. And so it has a diameter of 30 centimeters. And when played on a turntable, the record spins at 33 1/3 revolutions per minute. And we're to find the angular speed in radians per minute of the record as it plays. And we went around to the nearest tenth. And so first, just some kind of thoughts about this. So this is 33 1/3 revolutions per minute. So kind of just think about 1, 2, 3, 4, if I went around 33 1/3 times, that's what's happening there. And I'm asked about angular speed in this problem. And so my angular speed is theta divided by t. So our angular speed omega equals theta divided by t. And so in this one, our theta has to be, since our angle, it's going around all those times, we really have to figure our angle is going to be 33 33 1/3 times 2 pi, 1 full revolution. And so I'm going to change that 33 1/3 into an improper fraction. So 33 times 3 is 99 plus 1 is 100 pi, 100 over 3, and then times 2 pi. So that's going to be 200 pi over 3. So that's our angle theta. And notice it says radians per minute, and this was how many radians it made, or revolutions it made. So we can just say our time is 1 minute for this problem. And then back to here, I'll maybe change my color. So omega equals theta, which is 200 pi over 3 radians per 1 minute. And you know, if I'm going to want to maybe label that radians per minute, I'll just kind of write that little fraction in there as well. So omega is equal to 200 pi over 3 radians per minute. And then it's approximately, when we do that division or multiplying, 209.4 radians per minute. And we'll kind of leave that as is. Then, moving along, we're kind of talking in the same problem. Now we want the linear speed of the outer edge of the record as it spins. So now we want to consider that diameter, which is 30 centimeters. So really we want the radius, which is 30 divided by 2, or 15 centimeters. And our theta is that same 33 1/3 times 2 pi. So that's 200 pi over, that looks like 260, 200 pi over 3. So there's our theta and our r. And so then linear speed, if you remember, is v equals s divided by t. And now we're going to remind ourselves s is r theta divided by t. And so time again will be our 1 minute, but in this problem they asked us about centimeters but per seconds. So our time is 1 minute, but we're going to say our time is 60 seconds for this problem because of that wording as we go. So then I'll go back. So v equals r, which is 15 times theta, which is our 200 pi over 3, all divided by 60, and that is going to be in centimeters and seconds. So that's going to be in centimeters per second. So then if you want to take a minute, pause this, do that calculation, you can. And then I'm just going to give the answer. It's 52.4 centimeters per second for that one. And I know this is a very long lesson, but I am just going to finish up because our last thing is about a sector. And maybe you remember from previous work that, and let me kind of go, the sector of a circle is a region bounded by a central angle and its intercepted arc. So you can see in this little diagram here, and you might want to, you should draw that. I was going to say you might want to draw it, but now I'm just going to say please draw that. I'll put a little box around it, and you can just draw it once. It's below there as well. But when we have that sector, it's this little wedge region, and I'll use my yellow marker to kind of highlight in there a minute, and then I'll erase it. So the sector is kind of this little place there, and we're going to find the area of that. You can kind of look through that as you go, And I'm just going to write our rule. I'm going to write it to the side here. So our area is 1/2 r squared theta. Oops. There we go. And r is the radius. And theta is the central angle in radians. So really important that we are using radians as we go. If you were back in geometry, we kind of learned the way to find the sector of a circle a little bit differently, but it gave the same result, and we were using degrees back then. So area of a sector, here's that formula again, and maybe you've written it already, and just kind of that theta is measured in radians. So I think you're going to find these kind of pretty straightforward problems. So for 6a, we want to find the area of the sector there. Area is 1/2 r squared theta. So when we look at this picture, r is just 5 meters. Theta is 3 pi over 4. And so area is 1/2 times 5 squared times 3 pi over 4. And just a little reminder, that we have to square that 5, please excuse my dear Aunt Sally order of operations. We want to square just that 5, don't do half of that or anything. So it's half, or you could type it in as 0.5 and then put that 5 in parentheses squared and then times 3 pi over 4. Just remember to use your kind of good mathematics as you go. And I'm just going to give a decimal approximation of that to the nearest tenth, so you can as well. And it is 29.5 square meters, 29.5 square meters. And don't forget our labeling then with area, since it's radius times radius, is square units as we go. Last problem in this lesson, finally, hooray. So 6b. This one, same kind of thing. Area is equal to 1/2 r squared theta. Here r is 8 feet, and so just always look at the picture, make sure you know the radius, and theta is 60 degrees, but we know we have to convert that into radians, so we're going to multiply by pi over 180, and that is pi over 3 for theta. So then we'll just substitute that in. Area is 1/2 times 8 squared times pi over 3. Make sure that you're trying these on a calculator just to make sure that you're keying them in correctly. And if you want to pause this and check, go ahead. Otherwise, 33.5 square feet is the answer there. And that is this lesson. And I will just kind of say I went really long, so there are these problems, and if you want to try these and pause it and try each of these, you can. It is not necessary or mandatory, and then on the printed slides I'll have these worked out so that you can check your work. And there's number 2. You do have to pause this right away. Moving on, here's 3. Pause it if you want to try it. Here's 4, pause it if you want to try it. Here's 5, pause it if you want to try it. Here's 6, pause it if you want to try it. And then that's the lesson. So thanks for tuning in, and I will talk to you later.